we've seen the definition of the derivative in terms of a couple different limits. Let's use the definition to actually calculate some derivatives. Here's our first example. We want to use the definition of the derivative to find f prime of x when f of x is the polynomial 2x squared plus 1. Well, the definition of the derivative says that f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Well, so I plug in, I get the limit as h goes to 0. I plug in x plus h to the function. So I have 2 times x plus h squared plus 1 minus, and I always want to remember to put parenthesis around this second part f of x so that I remember to distribute the negative sign. F of x is 2x squared plus 1, and then I divide everything by h. So this gives me the limit as h goes to 0. I want to expand this x plus h squared. So either you can write down 2 copies of x plus h next to each other and then multiply them out, or some of us have the formula for this sort of thing memorized. So I get 2 times x squared plus 2xh plus h squared. Again, if you don't know where that came from, make sure you expand out this term here, plus 1. Now I distribute the minus sign, minus 2x squared minus 1 all over h. Next, I'm going to distribute the 2, so I have 2x squared plus 4xh plus 2h squared plus 1 minus 2x squared minus 1 all over h. Now, I look at what I have here. Here I have a plus 2x squared, and here I have a minus 2x squared. So these guys cancel. Here I have a plus 1, and here I have a minus 1, so these cancel. That means I'm left with the limit as h approaches 0 of 4xh plus 2h squared all over h. All the other terms canceled. Here, I notice that here I have an h in this term 4xh, and here I have an h in this term 2h squared. So I can factor out an h from both of those terms. 4x plus 2h. This is all over h. The reason that I want to do this is that now this h in the numerator cancels with this h in the denominator. I have the limit as h approaches 0 of 4x plus 2h. Now, because I don't have an h in the denominator anymore, I can go ahead and just plug in h equals 0. This is a polynomial, and we know how to evaluate the limits of polynomials. So this is 4x plus 2 times 0, or just 4x. So f prime of x is equal to 4x. Again, we could not plug in h equals 0 at the beginning of the problem because that would make the denominator 0, and we can't divide by 0. But with a little bit of algebra, we can reduce this function to something where we can plug in h equals 0 and get the derivative. In our first example, we took the derivative of a polynomial. The key to doing that example was expanding the polynomial, factoring out h from everything, and then canceling the h, and then finally plugging in the value. This is an important trick to remember. Anytime you see a polynomial, try to do this same process. Let's look at another example. Now let's tackle our second example. We want to use the definition of the derivative to find f prime of x when f of x is the function 3 divided by 2x. So again, the definition of the derivative says the f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So in this case, I have the limit as h approaches 0. I plug in x plus h everywhere I had an x, so that's 3 over 2 times x plus h, minus f of x is 3 over 2x, and then this whole thing is divided by h. Okay, so the next thing that I want to do is make this a little bit easier to write down. We remember that if I have something on the top and something on the bottom, I can write this as the top thing times 1 over the denominator. So I rewrite this as the limit as h approaches 0 of 3 over 2 times x plus h minus 3 over 2x, and this is all being multiplied by 1 over h. So this is the numerator, and this is the denominator. So I put 1 over the denominator, and I can multiply these two things together. All right, let's simplify this by distributing the 2. I have the limit as h approaches 0 of 3 over 2x plus 2h minus 3 over 2x, and everything here is being multiplied by 1 over h. All right, next, I have two fractions here, 3 over 2x plus 2h and 3 over 2x. It would be a lot easier to understand what was going on if I had one fraction instead of two. So I'll make a common denominator, and in fact, the easiest common denominator possible, and then combine these into one fraction. The common denominator that I'll use is taking this denominator and multiplying by this denominator. So I have the limit as h approaches 0. This first fraction I have to multiply by 2x over 2x. So this is 3 times 2x over 2x plus 2h times 2x minus, and here in this fraction it needs this denominator, so I multiply by 2x plus 2h over 2x plus 2h. So I have 3 times 2x plus 2h over 2x plus 2h times 2x. This is all being multiplied by 1 over h. You can see that if I cancel the two x's here and cancel the 2x plus 2h's here, I would have exactly what I had in the previous step. Anytime you do algebra, it's really good to make sure that if you go back one step, you still get the same thing. Let's expand this out. So I have the limit as h approaches 0 of 6x over 2x plus 2h times 2x minus 6x plus 6h all over 2x plus 2h times 2x, and this is being multiplied by 1 over h. Now this denominator and this denominator are the same, so I can combine these two fractions into one by just subtracting the numerators. I'm going to go ahead and put parenthesis around this numerator because we need to remember to distribute the negative sign. So now I have the limit as h approaches 0 of 6x minus 6x, put the parentheses, plus 6h all over 2x plus 2h times 2x, and I multiply by 1 over h. So this is the limit as h approaches 0 of 6x minus 6x minus 6h all over 2x plus 2h times 2x times 1 over h. Again, here's a 6x, here's a 6x. One is positive and one is negative, so they cancel. So what I have here is the limit as h approaches 0 of negative 6h all over 2x plus 2h times 2x, and then this is all being multiplied by my 1 over h. All right, now I have an h in the numerator and an h in the denominator, so I can go ahead and cancel those things. This leaves me with the limit as h approaches 0 of negative 6 over 2x plus 2h times 2x. Now, since the h in the denominator has been canceled, I don't have any problems anymore with plugging in h equals 0. That will not make the denominator 0. So now that I have eliminated that problem, I can go ahead and plug in h equals 0. So I get negative 6 over 2x plus 2 times 0 times 2x. So simplifying, this is negative 6 over 2x times 2x, or negative 6 over 4x squared, or simplifying a little bit further, negative 3 over 2x squared. If you know how to use the power rule, it's really a good idea to check and make sure that this derivative that we just got here, f prime of x, is the same thing that you would have gotten using the power rule. The important trick to remember from our second example, a rational function, is that we made common denominators and then factored out h and canceled. Let's see a third type of example. Here's our third example. We want to use the definition of the derivative to find f prime of x when the function is given by the square root of 5x. So, like the last time, the definition of the derivative says that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So in this case, I have the limit as h approaches 0, the square root of 5 times x plus h minus the square root of 5x all over h. Like in the last examples, I want to cancel this h from the denominator so that I can just plug in h equals 0 and find the limit. In order to do that, in this case, I need to multiply the top and bottom by the conjugate of the top. Here's what I get. The limit as h approaches 0 of the square root of 5x plus h minus the square root of 5x times the square root of 5x plus h plus the square root of 5x. These two square roots and these two square roots are the same, and they differ by which sign is in between. On the bottom, I have to have this 5 square root of x plus h plus the square root of 5x, so I make sure I haven't actually changed the problem, and I also had an h in the denominator before. At this point, it's a really great idea to pause the video and calculate what you're going to have in the numerator. Make sure you do the multiplication very carefully. Okay, here's what I got. The limit as h approaches 0 of 5 times x plus h minus 5x over the same denominator, h times the square root of 5x plus h plus the square root of 5x. Let's distribute this 5 in the numerator and see what we get. It says the limit as h approaches 0 of 5x plus 5h minus 5x over the same denominator, h times the square root of 5x plus h plus the square root of 5x. Here's a 5x, here's a negative 5x, and so they cancel. So I'm left with the limit as h approaches 0. On the top I have just 5h, and on the denominator I have h times the square root of 5x plus h plus the square root of 5x. And now I have what I was looking for, an h in the numerator, an h in the denominator. They cancel, and so I'm left with the limit as h goes to 0 of 5 over the rest of this denominator, square root of 5x plus h plus the square root of 5x. Now I don't have an h by itself in the denominator, so I don't have any problems with plugging in h equals 0. Let's go ahead and do that. Now I have the limit as h approaches 0. Oop, no, we're going to plug in. We don't need the limit. 5 over the square root of 5 times x plus h, which is now 0, plus the square root of 5x. So simplifying, we get x plus 0 is just x, so this is square root of 5x plus the square root of 5x. Since I have two of them, we'll combine them together and get 5 over twice the square root of 5x. This is the derivative of the function that we're interested in. In our last example, the important trick was to multiply the top and bottom of our fraction by the conjugate. This is another important trick to remember. Anytime you see a problem that has a whole bunch of square roots in it, this is a good idea to try. Make sure you do some more practice problems on finding the derivative using the limit definition. This isn't going to come easy at first. Also, if you have a question, make sure to post it on the forum.